a spring, that is, what is the potential energy? Or to be more precise, this is called elastic potential energy, which is stored in a spring. This spring, as we know, if we have taken a spring like this, all the surfaces are frictionless, and over here we have a mass. If we pull it like this and release it, then this will be oscillating within these limits. Within these limits, we pull it, release it, it comes over here, this attains a natural length, this block has a maximum velocity, then now this compresses this block and it is retarding, the speed is reducing, and now when it comes over here, this is fully compressed and this comes to a stop. So once again, this spring pushes it back and this is going like this. Comes over here, it has a maximum velocity, then when it goes over here, it stretches the spring. When the string is stretched, the string pulls it back. When it pulls it back, so it starts retarding. It comes to a stop over here. And this cycle, it continues. So what happens over here is, there is an interchange of energy, of potential energy, elastic potential energy of this and kinetic energy of this. When we pull it and release from here, then this has been pulled and some potential energy, elastic potential energy has been stored into this. When it has been stored into this and this energy can do work, as a result, this pushes this block over here. When this pushes the block over here, the velocity increases. That is, kinetic energy from here to here, it is increasing of this block. When the kinetic energy of this block is increasing, the potential energy, obviously, it is reaching its natural length. The potential energy of this spring is reducing. When it is going from here to here, this block is going from here to here. When it is totally stretched, all the energy is with this spring in the form of elastic potential energy. When it is over here, all the energy is with this as the elastic potential energy. When it goes from position number 1 to position number 2, when it is going over here, then the kinetic energy of this block is increasing, and this is increasing at the expense of loss of this potential energy of the spring. When it comes over here, then this spring has natural length. There is no elastic potential energy which is stored in this. All the potential energy has been given to this block in the form of kinetic energy. So now all the energy is with this block in the form of kinetic energy. Because of inertia, obviously it keeps on moving like this. When it keeps on moving like this, once again it starts compressing this spring. When it starts compressing this spring, the elastic potential energy of this spring is increasing, and this speed is reducing, that is, kinetic energy is getting reduced. So what is during from 1, 2 to 3, so from 2 to 3, what is happening is, it is giving its kinetic energy and changing to the potential energy of this spring, elastic potential energy. When it comes over here, the velocity of this block is 0. This is fully compressed now. This is totally compressed. This spring is totally compressed. At this situation, when it comes over here, when the velocity is equal to 0, kinetic energy of this is equal to 0, the whole energy is now with this spring as the elastic potential energy. So this is how the energy goes from spring to block, block to spring, and these transformations, they are taking place. But the sum total of this energy remains constant. Now we are interested in finding what is the elastic potential energy which is stored in such a spring which is deformed by distance x, or any distance it is deformed. When you say deformed, it may be that is what is the elongation or what is the compression. We will come to that it doesn't matter. Whether it has been elongated or compressed by the same distance, the potential energy, elastic potential energy of the spring will remain as half kx square, where k is the spring constant and x is the elongation or compression. Let's come to that. First we have to understand what is spring constant. You might have seen that in some pens, there are springs, they are there. In some jotter pens also, there are small springs. And we have also seen that is in big trolleys, at the back of that as suspension, there are huge, thick springs, they are there, which work as a shock absorbers. So what is the difference between these two springs? We say the difference is in their spring constant. When we say a spring has a spring constant of 10 Newton per meter, it means if we wish to, if this is the natural length, and I wish to extend it, if we wish to pull it by 1 meter, so you will have to apply a force of 10 Newton over here. That is in this spring, which has a spring constant of 10 Newton per meter. For every 1 meter elongation or compression, we have to apply a force of 10 Newton. And this, through this, the formula comes out to be F is equal to kx, and if we are bothered about restoring forces, it comes out to minus k. Let's understand first what is this means. So it means if a spring has a spring constant of 20 Newton per meter and you want, that is, to pull it by 3 meter. So suppose this is a spring, it has a k of 20 Newton per meter. It means for every 1 meter deformation you require a 20 Newton force. So F is equal to kx. I want 3 meter extension or compression. So k is 20 Newton per meter into x. X is 3 meter. Meter get cancelled. So it means 60 Newton. So if I apply a 60 Newton force onto this, then I can pull this by a 3 meter distance. And after that, when my hand comes over here, through the muscles, I am applying a force onto my hand, 60 Newton. Then this spring will also be applying a restoring force of 60 Newton in this onto my hand. As a result, now I can't pull it further. If I wish to pull it further, then through my muscles, I have to pull this hand with a greater force, then only the extension will take place. So this is the meaning of spring constant. Now let's say when F is equal to kx, it means with x, as the deformation takes place, the restoring force is changing. F is equal to kx, so it means this is a variable force. We are interested, let's say this is a natural length and we are interested, suppose we pull it by a distance x, then what is the work which is done when I am pulling this, applying this force in this direction, and this is displacement is also in this direction, then what is the work done, or what is the energy, what sort of work is done that gets stored into its elastic potential energy. So we are interested in one way to find the elastic potential energy of this spring which has a spring constant k. Let's say this is spring is k and there is already an extension of x. So as a result, now I have to apply F is equal to kx force in this direction. This kx force I am applying in this direction, so that right now this my hand, this is my hand, through the muscles I am applying this force. So this is also applying a force in this direction, and that right now this my hand or this point is in equilibrium. That is, net force is equal to 0 at this instance. Now with the same force I move this by a very small distance dx, that is differential element of length. It is so small that is almost equal to 0 but not equal to 0, and F is equal to kx is sufficient enough in the equilibrium position to just pull it by a differentially infinite length a distance dx. So work done by this force is going to be F dot dx. This is a variable force. So F is what? Kx dot dx. When you say dot dx, F and dx, they are in the same direction. So cos 0 is equal to 1. So the dw is like this. So what is the total work done? So total work done is integral of both the sides. So this is kx dx. Suppose initially the extension was 0 and we are taking from 0 to x, extension is from 0 to x or compression is from 0 to x. So limits, they are 0 to x. So it comes out to be k, this comes out to be x square by 2, obviously 0 to x. So that comes out to be half kx square. So this is the elastic potential energy which is stored in the spring. Always remember, when a spring of spring constant k is deformed by a length x, that is, be it compression, be it extension, then the energy stored in this spring is half kx square, provided we take this as a massless spring.